The Hubble Space Telescope has been part of this adventure, this epic adventure to study exoplanets, as is the Spitzer Observatory, joined by Kepler. In 2017, we're going to launch what is, in some sense, the follow-on to the Kepler mission, although Kepler is now in its K2 mission, still looking for exoplanets and doing other great science. But the Transiting Exoplanet Survey Satellite will be launched, which will continue this wonderful adventure that Kepler has been on. And instead of looking at 150,000 stars in the constellation Cygnus, in the direction of the constellation Cygnus, it's going to look at all of our nearest neighbor stars, many, many stars, to try and find out not only, now that we know that many, many stars, most stars have solar systems, it will be looking for who are our closest neighbors. And when we find those neighbors, there's an amazing exoplanet observatory called the James Webb Space Telescope that will give us the opportunity to follow up and do spectroscopy of planets and planetary atmospheres around nearby stars. And we even are starting to talk about plans for future observatories. Of course, James Webb Space Telescope will do much, much more than just exoplanet science. But we are on the cusp of a future observatory beyond James Webb that could get the spectrum of the atmosphere of an Earth-like planet around a nearby star like our Sun, and maybe look for signatures, potential signatures, biosignatures, indicating there could be life on that planet. It'll take a little bit of luck, a lot of skill, but we're on the road to do that. Today we're announcing the discovery of an exoplanet that, as far as we can tell, is a pretty good close cousin to the Earth and our Sun. This is about the closest so far, and I really emphasize the so far because the Kepler data set is very rich, and the team and the science community has full access to be able to extract future discoveries out of the data set. But today we're announcing the closest twin, so to speak, to Earth 2, or the Earth 2.0 that we found so far in the data set. And to describe that discovery, I'd like to hand it over to John Jenkins from the NASA Ames Research Center, the lead author on the paper.
Well, thank you, John. And welcome to all of you who joined us to hear this latest chapter in the unfolding story of NASA's search for habitable worlds. In the 6 years since we launched Kepler, we've made amazing progress in the search for the right-sized planet in the right-size orbit of the right-sized star. We're looking for small planets in the habitable zone of their stars, that region within which liquid water could pool on the surface of a rocky planet like Earth. In December 2011, with just 2.5 years of data under our belts, we announced the discovery of Kepler 20e, the first planet smaller than Earth orbiting a sun-like star. But it's so close to its star that it's scorching hot and cannot hope to hold on to an atmosphere, let alone a liquid water ocean. But in that same month, we announced the discovery of Kepler 22b, the first planet in the habitable zone of a sun-like star. But with a radius of more than twice that of Earth, it's highly unlikely to have a solid surface you or I could walk on. So the search went on. We collected more data. Just over a year ago, we announced the discovery of Kepler 186f, the first near-Earth-sized planet in the habitable zone of a small, cool M star, about half the size and mass of our Sun. Well, today, we're pleased to announce the discovery of Kepler 452b, the first small planet in the habitable zone of a G-type star very similar to our own Sun. So to introduce you to this planet, I'd like to show you an artist concept shown in Figure 4. Looking at this image, I'm reminded of a poem by John Keats on first looking into Chapman's Homer. Then felt I like some watcher of the skies when a new planet swims into its ken. Now this illustration draws upon the facts that we do know about this planet and its star. The star is the same surface temperature and type as the Sun, a G2 star. The star is 10% bigger and 20% brighter than our Sun, as it's somewhat older. And this planet orbits its star every 385 days and is just 5% farther from its star than the Earth. Now, with a radius 60% larger than Earth, this planet has a somewhat better than even chance of being rocky. To come up with this illustration, we consulted with planetary geologists and atmospheric scientists studying exoplanets to determine what this planet would be like if indeed it is rocky. It would likely have a mass about 5 times that of Earth and a surface gravity about twice that of Earth. So you and I would weigh twice as much as we do now, but only until we walked around for a few weeks and lost some serious pounds. We'd also expect the atmosphere to be thicker and have more cloud cover, and this planet would likely still have very active volcanoes. To put this discovery into context, let's look at Figure 5, which shows the Kepler 452 system alongside that of Kepler 186 and the solar system. The green shaded regions indicate the habitable zone in each system. Now, as you can see on this figure, Kepler 186 is clearly a miniature solar system. The orbits of all 5 planets, including the outermost, 186F, would fit inside the orbit of Mercury, which, as we all know, is not a habitable world. In contrast, the habitable zone of Kepler 452 is nearly the same size and extent as that of our Sun. Moreover, the size of the orbit of 452b is nearly the same as Earth. So to put this discovery in context with all the small confirmed planets less than 2 Earth radii in the habitable zone that we've discovered by Kepler in the last 6 years, I'm showing a scatter plot of all these planets on Figure 6 in terms of the surface temperature of the star they orbit on the y-axis, and in terms of the amount of energy received from their star in Earth units on the x-axis. The light and dark green shaded regions indicate the conservative and optimistic habitable zones, respectively. The blue disks indicate the sizes of these planets relative to one another and to the Earth, depicted here alongside Venus and Mars in the upper part of the diagram. Note that all the planets discovered before today lie in the bottom half of the diagram. That is, they all orbit stars that are significantly cooler and smaller than the Sun. Well, today the Earth is a little less lonely because there's a new kid on the block who moved in just right next door in terms of the surface temperature of the star it orbits and the energy it receives from its star. Now today, 452b receives 10% more energy than the Earth does, but that wasn't always the case. Figure 7 presents a window into time depicting the history of the habitability of Kepler 452b and the Earth. Stars are like people. When they're young, they're small and dim, but as they grow older, they fill out, slow down, and they get brighter. Here, we examine the change in the environment of Kepler 452b in terms of the energy it receives in Earth units on the y-axis and in terms of the age of its star in billions of years on the x-axis. When this star was young, it was only about 80% of its present size and 64% as bright. So the planet received 64% as much energy then. But as it aged, the star grew larger and brighter, as depicted in the inset, so that the planet experienced a steady increase in energy up to its present age of 6 billion years, where it's receiving 10% more energy than the Earth does. Now, it'll leave the habitable zone for good at an age of about 9 or 10 billion years as the star continues to grow. But it's very interesting to note that the Earth follows neatly in the footsteps of its older, bigger first cousin and will receive the same amount of energy as 452b does today in another 1.5 billion years. Now, at this point, the Earth may begin to experience a runaway greenhouse effect, according to models that scientists have to predict what might happen, reducing the water inventory substantially. Kepler 452b, on the other hand, is protected by its higher mass from this event for another 500 million years or so. I'd like to focus for a moment on the present age of 452b as depicted in Figure 8. It's simply awe-inspiring to consider that this planet has spent 6 billion years in the habitable zone of its star, which is longer than the age of the Earth. That's considerable time and opportunity for life to rise somewhere on its surface or in its oceans, should all the necessary ingredients and conditions for life exist on this planet. Well, let's round up all the small habitable zone planets discovered by Kepler in the past 6 years. As Figure 9 shows, we've detected 4 such planets orbiting M stars, which are significantly smaller and cooler than the Sun, and 7 such planets orbiting K stars, which are slightly cooler and somewhat smaller than the Sun. Today, we add the first small, possibly rocky planet orbiting a G star to this list. It has the same size orbit as the Earth and the same length year. It orbits the same type and temperature star and has a better than even chance of being rocky. It's a real privilege to be able to deliver this news to you today. Just 2 years ago, our hopes of finding Earth-like worlds were seemingly dashed by the loss of the second of 4 reaction wheels and the end of the data collection phase of the Kepler mission. It's been a real roller coaster ride all these years, from the many years we spent convincing our colleagues that we had the technology and the science was right to fly this mission, through that nail-biting episode of watching the candle being lit and watch the rocket take off, and then today. We also recognized at the time, early in the mission, that the Sun-like stars we were observing were more variable than the Sun, complicating our efforts to find the weak signatures of these small planets. but we worked really hard over the last several years to improve our planet hunting software, and we're seeing the results in this discovery. Now, given that every small habitable zone planet we detect corresponds to at least 50 that we can't see in our data because they're not aligned right, or we're not quite sensitive enough to see them, we can say that near Earth-sized planets in the habitable zone of Sun-like stars are common throughout the galaxy. Surely there are more gems like 452b waiting to be discovered in the rich Kepler legacy archive. To tell us more about newly identified planet candidates, I hand it over to Dr. Jeff Coughlin.
All right. Well, thank you, John, very much, and thank you all for being here to listen in. I am really excited today to announce Kepler's 7th Planet Candidate Catalog. So Kepler, over the 4 years of its main mission, collected a large amount of increasing data. And as it did so, we presented a series of catalogs to document all the planet candidates we had discovered. Well, 6 months ago, we presented the 6th catalog, which contained just over 4,000 transiting planets. Today, with the announcement of the 7th catalog, we've increased the number of those planet candidates by over 500. And I think this is particularly impressive because we only have 1 extra month of data. And in fact, that's the final month of data collected by the spacecraft on the main original Kepler field. So we're no longer finding new candidates due to collecting more data. We're finding them due to an improvement in our techniques. We're understanding the Kepler data better with every single day, and we're improving our ways to find the planets in those data.